This is the third lecture for the section 2.2, where we're going to talk about how to do calculations having to do with normal distributions. But we're going to use the website Desmos as our resource for learning how to do these easily. The notes in this packet are written for the TI Inspire calculator. I don't have them written up for Desmos yet, so that's why I'm making this video so that you can learn how to do these calculations easily. Um, we're going to repeat a calculation that we did earlier, and that is what proportion of Tiger's drives travel at least 290 yards, given that the drives are normally distributed with a mean of 304 and a standard deviation of 8. So I'm going to bring um, down a, uh, a tab, right? I'm going to go to Desmos, right? I'm going to open up the graphic calculator and ready to enter a command. I am going to go to the show keyboard and under functions, down, down in an area called distributions, probability distributions, there is a command called normal distribution. So I am going to hit that button and you'll see that the word normal distribution showed up there. Now, we can create the normal distribution that mimics Tiger Woods's uh, driving capability. It has a mean of 304, then we hit comma, and then we hit 8 for the standard deviation. And then what I'm going to do is I'm going to hit this little magnifying glass with a plus sign, and it'll take me to the part of the um, graph that actually shows this. You can see that it's centered at 304. It's got about the right standard deviation. Now, if I want to do a calculation like what percentage of the shot of his drives were at least 290, I'm going to click on this little triangle here and say I want to do cumulative probability. And then you can see that part of this is shaded in. Now we have choices for region and computation. For all the ones where we're calculating the percentages or the areas, we'll keep it on area. Um, when we're doing at least 290, well, that shaded in area would fill into the right-hand side. So I'm going to click on right, and then you see that the probability that X is greater than 304 is 0.5, but we wanted 290. So I'm going to click where it said, used to say 304, and type in 290 and hit enter. Oh, I'm sorry, that's supposed to be I typed in 209, I meant 290. And there we have it. There is the shaded in area like we expected and that number. Now, 0.96 isn't enough decimal places for me, so I'll click on the little arrow to get a larger number of digits of accuracy. I want 4 digits, rounded to 4 digits for our assessments. So there we go. There's the calculation of at least 290. What is it? What are you going to write on your paper? Well, you'll write everything that you see, like the normal distribution, and then P is greater than, and then that number, and you'll draw a rough sketch of this, and shade it in appropriately. All right, here's a second question. What's the proportion of Tiger Woods' shots that travel between 305 and 325? Well, that problem is an inner problem, meaning that we have a range of values, and our lower bound is 305 and our upper bound is 325. Hit enter, and you can see again that it shades in appropriately and then gives us the probability, and of course, down arrow to get the number of decimal places that we need. A third kind of problem that we did by hand was called the working backward problem. Um, we said, hey, we want to know what it takes to be at the 25th percentile for some particular distribution. The distribution was of cholesterol levels for 14-year-old boys, and it had a mean of 170 and a standard deviation of 30. Well, I'm going to get rid of our example here and start fresh. And for our working backward problem, we're going to go to our functions again. No, we're not. I'm sorry. We're going to go to our functions again. Yep. We're going to go to normal distribution. And this time we'll type in that again, the mean was 270 and the standard deviation was 30. And we'll hit enter and we'll hit the magnifying glass. And now we have a representation of that probability curve. Again, I'm going to choose cumulative probability, but instead of computing area, I'm going to compute bounds. Now, the bounds mean I'm going to give it the area. Our area, remember, we want to be in the 25th percentile, so I'll put 0.25. And I want the area to be, since it's a percentile, I want it to be the left-hand side. So if I choose left and bounds, it now tells me that 149.8 is the value that gets you to that 25th percentile. Again, if we want more decimal places, we click on that little down arrow to finish that off. Again, what are you going to write down? Write down what you see on all of this, and then make sure you make a sketch and shade it appropriately. All righty. Now, the last thing that's in this section is about assessing normality. Um, in our notes, we have some ideas about assessing normality, meaning we have a data set, we have great data tools for normal distributions, but we're not allowed to use them unless the distribution is normal, and not every distribution of a quantitative variable is normal. How can we tell whether the data set is normal or not? Well, we can start by plotting the data. When we look at the data, do the data look symmetric, bell-shaped? Then we can also ask, does it follow the 68, 95, 99, 7 rule? Right? And then lastly, we're going to do something called normal probability plots. So whenever we want to assess the normality of a data set, we can do all of these things. For example, here are some data, 50 states in November 2009. The data have to do with unemployment rates from the lowest 4.1 to the highest 14.7%. This was right after the Great Recession started in Michigan because the auto industry was really, really hurting at that time. So we can plot the data. Now we're going to do this in Desmos. Now in Desmos, if we want to plot the data, we start, I'm going to get rid of the old stuff, by adding a table. And that table by default is the columns of the table are X1 and X2. And I could start entering in the data, 4.1, 4.5, 5.0, etc. But that you don't want to see me entering data. So what I'm going to do is say that I already have a Desmos document with that data all already entered, all 50 pieces of data entered. Okay, well, let's take a look at these plots and see if we can assess the normality. Now, to make a histogram in Desmos, we'll go to functions and we'll go down the list until we see visualizations and we'll hit histogram. It says, what's the data set? The data set we called X1. And there you see the histogram. If I hit the zoom fit button, we can get an idea of what that histogram looks like. And we see, what do we see? Well, it's certainly sort of moundish, kind of bell-shaped, except for this little part here. So the question is this normal or not? Well, the general trend of this data is like a single bound. And, there's a little exception to this rule, but the general trend is that it's mound-like, right? So we're going to say, yeah, that looks okay. That looks okay. I'm going to hide the histogram and I'm going to go to another visualization, which is called um, the box plot. And again, my data set is X1, and we can hit that uh, zoom fit to see that data. All right. And by the way, if we have this checked, outliers will appear as dots. There are no outliers in this data set. So even though Michigan had really high unemployment, it wasn't an outlier at that moment. And what are we looking for here? Well, normal distributions are symmetric. So symmetry means that the lengths of the whiskers are approximately the same, and the widths of the two sides of the box are essentially the same. And a little bit of skewness here, but I would say not so much to be concerned about. I might say that this is not an indicator that it's not normal. All right. Now, for the last thing, before we go to the normal probability plots. In the notes, they did some calculations and said, hey, the mean of this data set is 8.682. The standard deviation is 2.225. And they said, well, how much of the data falls within one standard deviation of the mean? If you took the 8.6 and subtracted 2.2, you get about 6.4. If you take the 8.6 and you add 2.2, you get about 10.9. And if you set up those bounds, about 36% of the data set fall within one standard deviation of the mean. Now, if everything is normal, this should be about 68%. Is 72% about 68%? Yeah, it's about that. Okay. Within two standard deviations of the means, we got 48 out of 50, which is 96%. If it's normal, it should be about 95. That looks pretty good as well. Lastly, three standard deviations, we got 100%. Is that approximately 99.7? And we say, yeah, it's about 99.7. So therefore, we're going to say it seems like those are pretty close. And that again indicates normality. The last thing we do is that we could do something called a normal probability plot. Now, I'm going to tell you ahead of time, the TI Inspire does this really, really easily. But I have figured out a way to make Desmos give us a normal probability plot. And that normal probability plot, and I'm going to get rid of the box plot here, involves a few steps. So you're just going to have to deal with the fact that you're not knowing what all of these things mean at the point. But first of all, we say, I want, uh, what I want is Z to represent a normal distribution. So I can type in normal distribution. Actually, no, it's just normal dist. And I'm going to make this a standard normal distribution. All right, that's step one. Step two, um, we are going to say there's 50 states. So I'm going to create a list of numbers, and those list numbers are going to match up 1 through 50. So I'm making a list that has the numbers 1 through 50. Okay, that's second step. I could, in general, just call this 1 to the count in that list called X1. That works as well. All right. The third step is that we're going to make a third list. And that third list, I'm going to call Q for quantile. And the third list is going to have the numbers in it. And what I'm going to do is I'm going to translate the L list into something that's like a percentile. And I do that by making a fraction, taking every number from the L list, subtracting it by 0.5, and dividing it by the number of things in list one. And this creates a list of numbers, which is essentially um, not, uh, well, it's a list of numbers that represent, like the first number is at the first percentile, the second number is at the third percentile. Lastly, I'm going to do a graph. And that graph is going to be of all the numbers in X1 matched up with all the numbers in Q. Okay, let's get rid of that normal probability plot. And so I'm going to erase that. And you can see, let's see if I can zoom in on that. The numbers here are, they line up pretty well. They line up pretty well. Oh, I'm sorry, I made a mistake. I made a mistake. Um, this was not supposed to be just Q. This was supposed to be Z dot inverse CDF of Q. There we go. That's what it's supposed to look like. All right. And we can see that those dots do mostly line up in a line. If we want to compare them to a line, we can compare them to the line that matches up with the Z values for this list. And that would be X1, sorry, X minus the mean of X1. And we can divide that by the standard deviation of X1. So there's a line that we can compare the dots to, and those dots are pretty close to the line, which indicates that this set is approximately normal. All right. So that's what that looks like uh, us checking the normality of that data set. All right. Now there is an example problem having to do with guinea pigs. Let me put the guinea pig data on there. And this one I did the same basic procedure, and that guinea pig data. Well, let me hide all of this stuff for a second, and let's just take a look at the histogram for that data. All right. Let's do relative. And, okay. So how does that data look? Does that look um, um, about correct? Let me see if I can make it the bins a little bit bigger. Oh, need to make the comma up top and then the 10. There we go. Maybe it's a little bit easier to see it that way. Does that data set look approximately symmetric? The answer is no, it doesn't. Not even close. Let's hide that for a second. And let's see what does the box plot for this data look like? All right. Let me zoom in on that. And oh, now we can see that there's a whole bunch of outliers in this data suggesting that it's not symmetric, that the length of this whisker is much larger than the length of that whisker. And if it's not symmetric, it's not normal. Okay. And then again, lastly, I can take a look at um, the general trend for the normal probability plot. Here's what the line should be if it went through the line, and it's really off the line. It's totally not linear, and therefore we say that this data is not normal, or the data are not normal. All right, and that concludes on how you can use Desmos to, one, do normal calculations, and two, assess normality.